Hello all. In the previous tutorial, we have seen how to use Xilinx IP core, especially the Xilinx Fifo in your design. So in this tutorial, we are going to design an IP core which will be using these Fifos internally. So we are aiming to develop an IP for doing the merge operation. So merge operation is an important part in merge sort operation. You might have seen it, which is a algorithm for merging numbers. So this is the aim. So you are given two sorted arrays. Okay, so you already have two arrays which are already sorted. In our case, we are assuming ascending order. Your aim is to combine these two arrays and make it into a single array, and this single array should be also sorted in ascending order. For example, if this is my first array and if this is the second array, once I do the merge operation, this should be the resulting array. Now we are going to do a hardware IP implementation which will do this merging part, and the arrays which have to be merged will be sent from the processor to our IP, and when the processor reads back the array, it should get this merged array. Now this is the general algorithm for the merge operation. So I am taking the same arrays in the previous slide. So what you will do is you will always compare only the first element of both arrays, and whichever element is smaller, you will take it out of this array and put it in the new array which will store the merged array. So in this case, you compare 1 and 3, and 1 is smaller, so you take 1 out of here and put it here, so that this 5 will become the next first element of this array. Then you will compare 5 and 3, and 3 is smaller, and you will take 3 out of here and put here, so on and so forth. So you will continue this until either both arrays become empty or one of the arrays become empty. In our case, the second array became empty and the first array still has two elements. So whichever array is not empty, in this case you will continuously read from there, because there is nothing in the second array for comparison. You continuously read from the non-empty array and fill the merged array, and you will have the merged array. So this is the general algorithm for merge operation. So when we do the software development from SDK point of view, this is what we are going to do. The processor, it will first send the first array, and the address to which he will write is base address plus 12. Then he will send the second array, which will be base address plus 16. He will write to that address. Then the processor will configure the control register. We are assuming base address plus 0 register to indicate that the IP can start merge operation, that the processor has finished sending both arrays to the processor. And processor will keep on polling the status register, which we assume base address plus 4, to check whether IP has finished the merge operation. And once the status register indicates that he has finished merge operation, the processor will be reading back from address base address plus 8, and he should receive the merged array. And after that, the processor will clear the status register. So this is what we will follow when we develop the SDK. Now these are the register map, the addresses and the name of the registers, whether they are read-write or read-only, write-only, and what each register will be doing. Okay, so we have control register, status register, merge register, array 1 register, and array 2 register. Now, only one address per array is exposed to the processor for writing the two initial array as well as for reading from the merged array. But a single array will be composed of multiple elements. You have seen it. Okay, so whenever the processor writes to address C or 10, these two array 1 and array 2 registers, what we'll do is, instead of storing that elements in a register, we'll be internally storing them in two FIFOs. Okay, so internally it's a FIFO, but from the processor point of view, it will be seen as a single address. Now similarly, when the processor reads from the merged array, each time he reads from address 8, we'll be reading the merged array from a FIFO and sending it to the processor. Now, since this is a hardware implementation, there is no dynamic allocation possible in real sense. So we'll have to limit the maximum size of the arrays which our IP will support. So here we are putting the restriction: each array, array 1 and array 2, the maximum size is 1024, so that the merged array maximum size is 2048. So the array size can be anything less than 1024, okay, for each of the arrays. This is the state machine internally implemented by our IP. So initially IP will be in the idle state, and it will remain in idle state as long as the start signal is 0. The start signal is coming from the control register, which will be set by the processor once both arrays are sent to our IP. Then he will come to the compare state, and he will compare the output from both FIFOs, and whichever is smaller one, he will write it to a third FIFO, which is called our merge FIFO. So this operation keeps on continuing as long as either both FIFOs become empty or one of the FIFOs become empty. If both of them are empty, we will directly go to the done state, and we will make the done signal high here and remain in this state as long as the start signal remains 1. Okay, so eventually the start signal will become 0 that we will implement, and in that case we will go back to the idle state. So if we don't wait for the start signal to become 0, and if we directly go from done to idle state, you will be some kind of infinite state machine, because the previous start signal may be still 1 and you will continue going to the next state. So you should come to the done state and wait until this signal becomes 0. Now if only one of the FIFOs become empty, you will go to this state, flush FIFO, and you will continuously reading from that non-empty FIFO and keeps on writing to the merge FIFO. So once again both FIFOs become empty, you will go to the done state, and eventually you will go back to the idle state. Okay, so this is the theory behind it. Now we will see how to do the actual hardware implementation. So in Vivado, you can open any project, maybe either existing one or new one. Because I'm going to choose a create new IP. So I'm going to tools, create and package new IP, and I'm choosing create new Xilinx peripheral. Let me call it merge IP, and I'm going to store it in my IP repo. Remember to keep it inside another folder inside your IP repo. And Xilite number of registers. Okay, so from register map we can see we need 5 registers at least, so I'm making it 5. Next, and choose edit IP and finish. So the IP template comes up, which we have seen before. So if you wish, you can write your entire code in this file itself, merge s0xi.v file. Now if you write it here, the main issue is if I want to simulate my IP, if I want to send data to my IP, or if I want to read data from my IP, I will have to follow the AXI protocol, because this module has AXI interface, okay, which is slightly complicated. We won't be able to do it only using waveform forcing. We may have to write some test bench. That is one reason I won't write it directly here. Another reason, again, it is always better to keep hierarchical design, okay, for finding up bugs and for simulation purpose. So the entire merge IP core, the core logic, I'm going to write it in a separate Verilog file, and I will finally instantiate it here. Okay, so I'm going to add a new source, and I'm calling it merge core, just like core of the merge operation. Okay, and in this case he will not directly show where to save your file. So what you should do is you should go to this project, wherever is your current project. So this is our merge, edit merge here you will see a folder called HDL. Again, you can store it wherever you want, but it is a good practice you put it inside the HDL folder inside your edit IP project. Okay, so let me keep it there. Okay, and finish. Okay. Okay, so let me first write the interface. So we'll of course need a clock, we will need a reset, we will need the start signal as per the state machine to start our state machine, and there will be one interface through which the data will be coming from the processor. Okay, so I'm just calling it FIFO write data. This will be stored in FIFO, but we have two FIFOs actually for storing that initial arrays which have to be merged. Okay, so to which FIFO it should be written is designated by two control signals. Let me call them FIFO1 write enable and FIFO2 write enable. So this data will go to both FIFOs, but only one of these signals will be high at a time. So based on that, it will get stored in that corresponding FIFO. Now finally, processor will have to read from the merge FIFO. For that, he is going to use merge FIFO read enable. He will read through it, and we have to provide the merged FIFO data. So I'm going to send it through this signal, and finally we have the done signal, which is coming from the state machine saying like I have finished. Fine, so this is the interface. Okay, so next thing what I would do is, anyway, I know I'm going to store my data in FIFOs, and the merged data, that is also I'm going to store in a FIFO. So let me go ahead and instantiate those FIFOs here. Okay, so I will go to IP catalog and search for FIFO. We will use Fifo Generator. Okay, let me make the first FIFOs where the processor will store data. I have to make only one of the FIFOs because I can just make one FIFO and instantiate it twice, which represents two physical FIFOs. But the merged one I have to instantiate separately because our assumption is the first two FIFOs are 1024 in size, remember, and the merged FIFO is 2048. So there is no way to directly parameterize it here, so you have to use the IP core generator twice. So this I'm going to call it array FIFO. We are using native common clock block RAM. Okay, all those remain same. Write width, okay, we are going to use everything 32-bit, and the depth is 1024, and read is also 32, this one. Now reset, okay, let's keep it there. Yeah, everything else remain default. Now as per the algorithm, if you see, I have to compare the first two elements of the array, or in this case our first data coming out of the FIFO, and whichever is smallest, I need to take it from the array and put it in the merged array. Okay, now in the traditional FIFO, what happens is you will get a data from the FIFO only when you make the read enable signal high. So here you have read enable signal high, and again remember there is one clock latency, so you will make read enable high. Only in the next clock the FIFO will see it, he will give the data, and only in the subsequent clock you can take it from the FIFO. Now you can definitely do it using this FIFO, but the implementation will be a little bit tricky. Now instead of that, if I choose this option, first word fall through, my implementation will become much easier. So what happens in first word fall through is the FIFO will prefetch the next valid data from the FIFO, and he will keep it at the output. Okay, so even if you don't make read enable high, whichever is the next valid data in the FIFO, the top of the FIFO, he will prefetch and he will keep it here. So when you make read enable high, what happens is he will actually prefetch the next data. So effectively, you see here read latency is 1. Once I choose first word fall through, you will see like the read latency becomes 0. Okay, so the valid data is already available at the output of the FIFO even before you make read enable high. So that's why he's saying latency is 0. So this will make my implementation much simpler. Okay, so that's why we are choosing this option, first word fall through. So remember, if you choose this option, the FIFO prefetches the next valid data and he will keep it at the output. Okay, so choose OK, and he will create the FIFO, generate, and while he's running it in the background, you can already go here and take the instantiation template from there, and we can actually instantiate it. So that I'm instantiating here. So as I said before, we need 2 FIFOs for storing 2 initial arrays coming from the processor. So this one, let me call it array FIFO1, and this one we will call it array FIFO2. Now we can do some of the port mapping. So clock is both common for both. Reset, again we are assuming active high reset, and both FIFOs are using active high reset. FIFO write data, this is the data coming to the FIFO. I'm connecting it to both FIFOs. That doesn't mean all data goes to both FIFOs. Which FIFO will store the data depends upon this control signal. So I'm keeping FIFO1 write enable here, FIFO1 write enable here and FIFO2 write enable here. Now the read enable, we will use it later because the state machine will be basically reading from this FIFO. So for the time being, let me disconnect them. D out, okay. That also will be used by the state machine. Full, we are not going to use it at all. We are not checking whether the FIFO is overflowing. Maybe we can put the restriction in software so that the processor doesn't write more than 1024. Or if you wish, you can connect this to the status register so that the processor checks the FIFO status before sending data to the FIFO. Anyway, in the state machine, we are not going to consider this full one. Now, empty, that is also used by the state machine. Okay, so when necessary, we will add those signals. Now, let me build the merge array or merge FIFO where we will store the merged result. So same way, you can go to IP catalog, again choose Fifo generator and choose merged, let's call it merge Fifo. And this is also first word fall through. All settings same except the depth is 2048. Generate. Take the instantiation template from here and instantiate. Let me call it merge Fifo itself. Same clock, same reset. Now the data to this Fifo will be given by the state machine, so we will keep them disconnected for the time being. Read enable, so finally processor will be reading from this Fifo. So that signal we already have here. Merge Fifo read enable. Let me connect it here. And merge Fifo read data. This is the data going to the processor. Okay. Full and empty again. For this Fifo we won't use. There is no way the Fifo will become full because his capacity is double that of this one. And empty, again we don't care whether this Fifo is really empty or not. Okay, so that's about the instantiation. Now we can go ahead and start writing the state machine. So we'll use the standard style of state machine. Begin end. If we are in reset state, we will be in the idle state. Remaining signal we will add as we go along. Else, begin end. We have case state, end case, and we are in the idle state. Okay, so as per our diagram, we are in the idle state and we will remain in idle state as long as start is 0. Once start becomes 1, we will go to the compare state. So start we have already declared here. So we can just write if start. We will change the state to compare. Okay, in the compare state, what we should do. Okay, so in compare state, there are different cases. One is, as you can see here, when you're doing comparison, maybe both FIFOs are empty, only one FIFO is empty, both are not empty. All different cases we have to write. Okay, so first case I am saying, if both FIFOs are not empty, that means there is some valid data at the output of these FIFOs. So we can compare them and we can find out whichever is the smaller one. So if FIFO 1 is not empty, okay, so this is the signal I'm going to use, FIFO 1 empty. So let's go ahead and connect it here. Empty, FIFO 1 empty here, FIFO 2 empty here. Let's declare them also. They are connected to the output of FIFOs, so they should be wire type. FIFO 1 empty and FIFO 2 empty. Okay, if both are not empty and not FIFO 2 empty, begin. Remember, we are using first word fall through. That means the output from the FIFO is already a valid data. You don't have to make the read enable high. Okay, the output from FIFOs are already valid, so you can directly compare them. If FIFO 1 data is less than FIFO 2 data, okay, that is the first case. So data from first FIFO is smaller. So what you should do, the data from the first FIFO should be written to the merge FIFO. So let me write merge FIFO data is whichever is smaller one, FIFO 1 data, and we have to write it to the merge FIFO. So the write enable of merge FIFO should be made high. So let's write merge FIFO write enable is 1 dp1. So what we should do, we should connect the signal. So merge FIFO write data, which is this one. The in is merge FIFO data. Need to declare wire. No, we are using it internally. Site always block. So reg type merge FIFO data and write enable again inside always block. Write enable. Write enable. And that is one case. Okay. Now else, that means FIFO 2 is greater than or equal to. Both we are covering. Both should be covered. So in this case, just the opposite. Merge FIFO data will be FIFO 2 data and write enable. Okay. You have to. Now what you should do, both FIFOs are not empty, so you asked to write them, compared them, you made the write enable high, then you have to read the next data from the FIFO, as well as you need to write it to the merge FIFO. So we have made the write enable signal high, and it should be made high only for one clock cycle, otherwise same data will get written multiple times. Also, you have to get the next data from the FIFO. If you want to get the next data from the FIFO, you need to make the read enable high. Okay, you need to make the read enable high, and on the next clock he will prefetch the next data, so that in the subsequent clock you can actually compare them. So to do all of them, we need to go to the next state, like in the state machine. So let me write state is write, and as I said, you need to fetch the next data. So in this case, you are reading from FIFO1. Okay, so next data should be prefetched by FIFO1. So FIFO1 read enable should be made high. So I will say FIFO1 read enable is 1 tick P1. And similarly, if you read from FIFO2, you need to prefetch next data from FIFO2. So FIFO2 read enable should be made high. So we can connect them here. FIFO1 read enable, and this is FIFO2 read enable, and we can declare them again. They are registers. Fine. Now we are going to the write state. So in write state, what you should do, you made the read enable high, and in the next clock he will see it, and you should make it back to 0. So we don't care which read enable was high in the previous state, we are making both read enables 0. So that whichever was high, it becomes 0, which was already 0, it remains 0. Same way here, FIFO write enable was high, that means next clock he will write it into the FIFO. So after this clock edge, this should be made to 0, and you will go back to the compare state like here. So all those things we did in write, and we are going back to the compare state. So state is back to compare. Okay, but compare state is not completed. We looked at only one case when both FIFOs are not empty. Okay. Now next case possible is if both FIFOs are empty, that is FIFO1 empty as well as FIFO2 empty. If both are empty, here we have it. When you're comparing both are empty, you can directly go to the so-called the done state. Okay, so we can go to state is done. We can write done state now itself. Okay, so what should happen in done state? Done state. So in the done state, we will make the done signal high. Done signal high. So we'll make a done 1 tick B1, and we will remain in this state as long as the start signal is high. So once the start signal become low, we will make the done signal back to 0, and we will go back to the idle state. You don't have to explicitly write if start is high, remain in done. So this implicitly states that that is the case. Only if start is 0, you will go back to the idle state. Okay, so that's about that. And the next possible case is only one of the FIFOs is empty. Okay, so else if FIFO1 empty. Since you have the condition FIFO1 not empty, FIFO2 not empty at the beginning, and FIFO1 empty, FIFO2 empty here, this implicitly means FIFO1 is empty, but FIFO2 is not empty. So what you should do? So remember, FIFO1 is empty. That means you need to keep on reading from FIFO2 and writing to the merge FIFO. Okay, so we'll make a FIFO2 read enable high in this case because 541 is empty. Similarly, else if 542 empty and 541 is not empty, again we will go to the same state, flush 54, but you will keep on reading from 541 and keep on writing to the merge 54. Okay, so you made this signal high, and he will see the signal only in the next clock. But this 54, he has already prefetched some data, and it is actually available at the output at this point of time. So in the flush 54 state, again what you will do is similar cases. If both are empty, 541 and 542 are empty, this one, if both are empty, you can go to the done state and maybe you were reading from 54 some 54 in the previous state, so we need to make all of them 0. So 541 read enable should be 0, 542 read enable should be 0, and in the previous case you might be writing to the merge 54, so that signal should be also made to 0. Then you will go to the done state. Else if only 541 is empty, like this case. So you keep on again reading from 542 and you will remain in the same state. But remember, you are coming from this state to this state. So this 54 already has some data at the output, the prefetched one, that should be written to the merge 54. Okay, so we need to make merge 54 write enable 1 here, and merge 54 data 541 is empty, so it should be data coming from 542 data. Same scenario if 542 is empty, 541 read enable. Even if you don't have the signal, it's perfectly fine because we are making them high in the previous state, so they will remain high as long as you don't make them low. 54 read enable, but 542 is empty, so this will be 541 data. That's it. So that completes our state machine. Now a lot of errors they are showing because we have to declare a lot of signals. So first thing, state. So we have 1 2 3 4 5 state, so we need 2 bits for state. So let's make reg 1 down to 0 state, and all the states we have to declare as local param. Local param idle is dt0, then we have compare is dt1, then we have flush 54 dt2, then we have write dt3, then we have done dt4. Okay, now 541 data, 542 data, these we have to declare. Okay, 541 data is the output from the first 54, this is the output from the second 54. They are outputs, so they should be declared as wire type. They are 32-bit wide, 541 data and 542 data. Okay, similarly done signal. Okay, that is inside state machine, so this should be declared as the reg type. Another thing, inside reset, we need to initialize all the control signals, okay, like our 541 read enable, 542 read enable, all of them should be initialized to 0. And merge FIFO write enable, only the control signal, not the data signal. Data signal you can initialize, but not mandatory. And so these two are controlled. Similarly, our done signal is also a control signal. So done also. Okay, so that completes our core logic for merge operation. Now we can go ahead and simulate and see whether it is really working or not. So for simulation, first you should go to settings and choose the top module for simulation, because we have multiple modules here. So go to simulation and top module, give it as merge core. Okay, and run simulation, behavioral simulation. Okay, so the waveform window, it shows the top level signals from the merge core. Let's add the signals from these FIFO sources so that we can see what is happening inside the FIFO. So new divider, array FIFO1, and I will add the signals from here, and array 2. And finally the merged. Okay, let's restart simulation. Play the clock. Let's give 100 megahertz, 10 nanosecond, and let's keep the reset applied initially, and all the control signal to low value. So start we will make 0. Write data doesn't matter, but let's put 0. Write enable 0 to both FIFOs, and read enable also 0. Okay, so let's run for a few clocks. Okay, so let's remove the reset signal. Now let's write to the first FIFO. So I'm going to use the same values that we have here. I'm first going to write these values to the first FIFO, then I will write these values to the second FIFO. Okay, so I'll make a FIFO1 write enable high, and first data is 1 1. Okay, first constant 1, and let's run for 1 clock. So next data is 5. 1 5, then 6 and 9. Sixteen, 25, 32. Okay, so after that I can make a FIFO write enable low. Okay, so if I go to the signals going to 541, you can see so same signals are going to 541. And if you look at the empty signal, you'll see at this point empty got deasserted. Okay, so it's not happening on the next clock itself, so there is some latency between we write data to the FIFO and when the empty will get deasserted. But one interesting thing is this D out, you can see it already became 1 because it's a first word fall through. So he prefetched this data and he already kept it at D out even before read enable is high. So same way you can write to the next FIFO, so you need to make 542 write enable high and 35710. Twelve and 20. Okay, so in a real case, the processor will be writing these values through the X interface. Okay, so same data should be going to the second FIFO. So you'll see the first data is also coming here, but the write enable signal is low because we connected the same data signal to both FIFOs directly. And the same data. Fine, and his output already became 3. The next signal that we have to assert is the start signal because you have already filled both FIFOs. Now you can ask the state machine to run. For that we will make the start signal high. And now the state machine should be running. You can see the states should be changing. You can see 0, 1, 3. It keeps on running. I'm not checking whether each state is correct. I'm running it until the done signal becomes high. So you can see he's writing something to the merge FIFOs. He's reading from different FIFOs. And here you can see the first FIFO, FIFO2 became empty. And after that he kept on reading from FIFO1. And finally FIFO1 also became empty. And the done signal also became high here. Okay, that means he finished the merge operation. Now in a processor scenario, what should happen is he'll be stuck at he went back to idle state here. So you can see he from state 2 he again went back to idle state. It shouldn't be happening as per our state machine. So if I go and check my state, I can find the error here. So I made the state only 2-bit. That means it can take values only from 0 to 3. You have value till 4. So this should have been 2 down to 0, 3-bit state. Okay, now you have to relaunch the simulation and rerun, but I hope things are working. So what I'm doing is trying to read from the merge FIFO and see whether data is coming out or not. Okay, so in this case, what happened was he didn't go to that done state. Instead, he directly went to the idle state back. But he's no longer writing to the merge FIFO because both array FIFOs are empty. So the data should be already in the merge FIFO. So let's see. So here data is coming out of the merge FIFO. Okay, so let's see what data is coming out. It is 1. Again, this is first word fall through. So although you are making read enable high here, the output is already valid here. So it is 1, 3, 5, 5, 6, 7, 9, 10, 12, 16, 20, 25, 32. So if I compare it with that, that is exactly the order. So our state machine is working. Only issue was the bit width was less. That was a mistake. So we need to make it 3. Now if you rerun from the beginning, everything will work. Only thing is your state machine will be stuck at this done state until the start signal becomes low. Because of my error, what happened was from compare state, he directly went to the idle state. Okay, so looks good. So we can stop simulation. Okay. So next I'm going to instantiate this merge core into my IP template. So I will copy it from here and I will put it inside this logic, maybe towards the end. And let me call it merge core. Some signals we can already connect. Clock signal we can directly connect to the XE clock. Reset, this is active high, but XE reset is active low, so we need to invert and connect it. Start signal, okay, so if you look at the architecture, start signal should be coming from the control register, this one. So we are going to connect the 0th bit of control register to the start signal. Okay, so what should happen is when the processor writes to address 0, which is our slave reg 0, the bit 0 will be connected here. So I will take the slave reg 0 and I will assign something like FSM start equal to 0th bit of this register, and this FSM start I will declare it as a wire, and I will connect that signal here. Now the requirement is something like that. So the processor will write 1 to this control register, it will start the state machine, and once the sorting is over, your hardware should clear this bit. Okay, so this is like set by software and cleared by hardware. So we need to look at the logic where processor is writing to the slave reg 0, that is this one. So as per this logic, only processor can write to slave reg 0, but our requirement is processor will be writing to it, hardware will be clearing to it. So I am moving slave reg 0 out of this always block and I am keeping it outside, and I will say okay, so this condition is same as before, slave reg write enable, and XE address is 0. Whatever data is coming from the processor will go to slave reg 0. But at the same time, once the state machine is done, which is indicated by this signal, done signal. So let me connect a wire there. So done. Once this signal is high, it should clear the control register. So this is how I am going to modify it. So if this condition happens, I will directly make the slave reg 0 to 0. Else if processor is writing, whatever data processor is sending, I will write here. So the hardware clearing has higher priority over software writing. Okay, that's it. And you need to remove slave reg 0 from everywhere here. Otherwise it will give multiple drive error later. Okay, so that one is taken care. We need to declare it. It is an output from our IP, so it should be declared as wire type. Next one is Fifo write data. So the data coming from the processor should be going to the FIFOs. So I will directly take the XE data, write data, and I will connect it there. So I will take XE write data, and I will directly connect it here. Now FIFO 1 write enable, the requirement is only when the processor writes to address C, that data should go to the FIFO 1. So here we have the code. So this address you need to divide by 4. So this is 12 by 4, 3. We need to see where 3 is here. This is the case where processor is writing to this particular address. So this I am going to modify. So what I will say is something similar to this. I will take this and I'm going to call this signal FIFO1 write enable. If reset is the 80, else if processor is writing to address 3, in that case I will make this signal high. In all other case, this signal will be 0. Okay, so whenever processor is writing to address 3, so here it is 12C, this signal will become high. We have already connected the write data to that FIFO input, so this signal will also go to FIFO and the XE data will get stored in the FIFO. So FIFO 1 write enable we will connect here, same way FIFO 2 write enable we will connect here, and we will declare both of them. They are inside always block, so reg type FIFO 1 write enable and FIFO 2 write enable. Now instead of a register I have replaced it with a FIFO, so you can remove this slave reg 3 from here. So slave reg 3 can go. And same way this will be 16 and here it is slave reg 4. So same logic you can replicate for FIFO 2 write enable. FIFO 2 write enable when the processor writes to address 4. So this can also go from here. We don't need those registers. Even if you keep them there, it's perfectly fine. When the processor is writing, it will go to the FIFO as well as it will get stored in some register. But for saving some resources, some flip-flop, you can just delete them from here. You can delete the declaration also. Even if you don't declare, remove them, the tool will automatically remove it when it finds like you are not using these registers here. Fine. So next signal here is merge FIFO read enable. Again, look at the requirement. When the processor reads from address 8, so here address 2, it should be reading from the merge register. Okay, so we have to create a signal here. Let's call it merged FIFO read enable, and this signal should become high only when the processor is reading from address 2. Okay, so we can simply write an assign statement for that. Assign merge FIFO read enable equal to, this is the read logic. So this is basically saying processor wants to read, and the address is reading from is equal to 2. This is enough. You can either write this way or you can write this way also, but this is sufficient. So only when the processor reads from address 2, this signal will become high. In all other cases, this signal will remain low. So we can connect that, and again assign statement, so declare as a wire. Now we have merge FIFO read data. So when the processor is reading from this address, it should get the data from the merge FIFO. Now, if you look at the code here, when the processor is reading from address 2, he is going to get data from slave reg 2. That is not the case. He should get the data coming out of this FIFO. So simply connect this. Again, this logic will work only if your merge FIFO is also first word fall through. Otherwise, there will be issue of delay, 1 clock latency. Again, you can do it with that, but the code will look a little bit more different. Okay, so this also we need to declare. It's an output, so it should be wire type. And status register, that is the only remaining thing. So remember, status register, it should become 1, the least significant bit, when the done signal becomes high from the state machine, and the status register will be cleared by the processor from the software. Okay, so usually again status is set by hardware, cleared by software, but control register, it is usually set by software but cleared by hardware. Now the status register is 4, that means address 1 here, this one. So instead of only processor writing to it, we need some processor and hardware. So processor, yeah, and state machine. So we'll take it from here, and slave reg 1. So initially it is 1. If sort done, slave reg 1 will become 1, and when the processor is writing to address 1, whatever the processor is writing will come to that register. So you can remove this one also. Now slave reg 2 here is address 8, okay, which represents the merge FIFO. Okay, so the processor is not supposed to write to that merge FIFO. That's why it is written. This is only a read-only address. Processor is only supposed to read from that register. So in this particular implementation, if the processor writes to that address, what happens is it will get stored in this register. But when the processor reads from address 2, we have already changed our logic. He is going to read from the FIFO. So this is a redundant logic here. You don't need this register. So effectively that entire always block goes away. Now reading part, okay, 0 from control register, 1 from status register, this from merge FIFO, 3 and 4, which are 12 and 16, these two registers. Processor, it is only supposed to write to those registers. He's not supposed to read from that because these are the internal FIFOs. So as per current logic, he will try to read from these registers. By default, they will be 0, so he'll always get 0. So you can actually remove that also to save some resources. Okay, so this completes our entire IP design. Now you can simulate this entire logic, but as I said before, the only thing is you will have to follow the AXI protocol for reading and writing from this entire IP. So you can either do it, or now you can directly put it in hardware and check it. If it is not working on hardware, you can put the debug core and try to debug it. Okay, so now we have to repackage it. So we go to component.xml and merge file. Now if you look at the sources here, you'll see he actually included your core, this Verilog file, and these two template file. Unfortunately, he hasn't included the files for the FIFO. Okay, these are the .xci files, Xilinx core inserted file. These files should be also made part of your IP. Otherwise, later when you implement, Vivado will give an error saying like he cannot find the source code for the FIFOs. So he's not automatically doing it. I don't know, maybe in the new Vivado, he may be automatically doing it. So what you should do is you should go back to tools and create and package IP. And this time you should choose package your current project next and choose include XCI file. Okay, so once you do it, you will see those files are also made part of your IP. Okay, so it should be done like this, otherwise later it will give error. Okay, so you are done. Now you can close this project and open a new project and add this IP and test it. Okay, so I'm going to start a new project. Let me call it merge test subdirectory. You can close this project. First thing, I am adding my repository here where I have kept all my IPs. Okay. Okay, next we will add our merge IP. Merge. Just choose connection automation. So this is like all our previous project. One thing that we could have done is synthesize this merge IP from our previous project just to check whether there are any syntax errors. Okay, that would have been good. Otherwise, if there are some syntax error, you will get error now. So we have to go back and correct it there and repackage the IP. So let's hope there are no errors. And let's go to address editor. Everything looks fine. So you can create HDL wrapper. and you can choose IP and choose generate output project products. Okay, once that is over, you can export your hardware to SDK. Export hardware. Okay, we are not including bitstream. You can see parallelly he's running the synthesis for the individual IPs. Once they are completed, you can start bitstream generation. But I can start developing my software in parallel. So I'm launching SDK. Okay, once SDK comes up, we can start a new application project. Let's go to source, new C source, and match test. I'm not writing it as a driver, I just want to test the code. If you are interested, you can make it like a proper driver. Okay. Let's include experimenters.h. So I'm going to use the same example for testing also. So first I'm creating these two arrays. So you will say 32 is my first array. My second array. I'm sending the first one to my IP for int I 2, 3, 4. Address is base address plus first array C. Now we will send the second array, which is 1, 0. Next we need to set the control register to start. So we'll say base address plus 0, base address. We set the control register. Now we need to wait for the status register to become 1. So let's say U32 status, and status is still in 32. Base address plus 4 is our status. This one plus 4, and while status is 0, we keep on doing this. And once status register becomes 1, we will read it and store it in another array. Let's call it U32C, whose size will be the sum of these two, 13. C of I equal to sil in 32 base address plus 8. And finally let's print it. Or you can print, actually you don't have to store it, you can directly print it if you wish here. Okay. Okay, so that's it. So this makes our basic software. Io.h, and this gives our basic software. Now parallelly you need to generate bitstream, and once it is completed we can test it on hardware. Anyway, bitstream generation is completed, so I'm programming my hardware first from Vivado because we didn't export the bitstream to SDK. I'm setting the tarata. And in SDK I'm making new run configuration. And I'm directly running it. And you can see the result here, which is exactly the same as the expected one and the same as the one in simulation. So I hope this gives you an idea of how to build your own IP which uses other Xilinx IP internally, and how to build a complete system. Thank you.